Okay, let's get started with writing some definitions of functions over lists. In order to do that, we're just going to think a bit longer about how lists are built. And the point I wanted to make was that every list can be built up from the empty list using a constructor cons. We called it cons. Remember, it's written as open square parenthesis, element, vertical bar, list, close square bracket. So if I give you the list 2, 3, 1, let me show you how it's built up in that way. Well, what is it? It's the whole list is 2 cons the list 3, 1. What about the list 3, 1? Well, that is 3 cons the list with just 1 in it. And what about the list with just one in it? It's 1 cons the empty list. So there you can see that this list 2, 3, 1 is 2 cons 3 cons 1 cons empty list. So everything is built up by adding elements to an empty list. And so we can use that insight when we define a function. So our template for recursion over lists is to say, here's the answer for an empty list, and here's the answer for a list x cons x's using the answer for x's, because we know that every list is built up by sticking an element on the front of another list. We just saw that in the previous example. So we give the answer outright for an empty list, and we give the answer for x cons x's in terms of x's. So let's take a particular example of summing a list of elements. So if we have an empty list, what's the sum of no elements? Well, the answer is it's nothing, it's 0. But what about the sum of a list whose head is x and whose tail is x's? Well, the key step is to think, well, if I know that the sum of 3, 4, 5, say, is 12, and I stick one more element, 2, on the front, then the sum of that whole thing is 2 plus 12. It's the first element plus the sum of the rest. And there we see that what we say is sum of x cons x's is x plus the sum of x's. Again, it's a recursion, very like the pattern we saw for numbers. We give an outright answer for the empty list, and in the case of a non-empty list, we say calculate the answer for x cons x's in terms of the answer for x's. Now, we'll see there are other patterns for recursion, other ways that we can do recursion, but this is the main one. This is the one that we'll use most often. So that's the key step. Now let me just show you that we can use this as a way of evaluating. This describes, if you like, it's a very direct description of what the sum is. It says the sum of an empty list is 0, the sum of x cons x's is x plus the sum of x's. And we can use those equations to write out a calculation. So we can do it with the list 2, 3, 4, 5. We start off, we've got to sum 2, 3, 4, 5. Well, the first case doesn't match, the second case does. X matches 2 and x's matches 3, 4, 5. So we get that is the same as 2 plus the sum of the list 3, 4, 5. Now, we haven't got the answer yet because we don't know the sum of 3, 4, 5. So let's work that out. Again, the second clause tells us it's 3 plus the sum of the list 4, 5. Again, we have to find that sum of the list. So the sum of the list 4, 5 is 4 plus the sum of the singleton list, the list with just 5 in it. And again, that still matches the second case there. So in this case, x is 5 and x's is the empty list. So sum of the list with just 5 in it is 5 plus the sum of the empty list. And now we're in a situation, we've hit the base case, sum of an empty list is 0, and so we have the answer is 2 plus 3, oh well, it's 5 plus 0 is 5, plus 4 is 9, plus 3 is 12, plus 2 is 14. So we get that the sum of the list of numbers is 14 using that definition. Okay, so that was a direct recursion. It tells us what the sum is. You remember we talked about this when we talked about recursion over integers. It says the sum of an empty list is 0. The sum of x cons x's is x plus the sum of x's. But we can also do it tail recursively. Remember we talked about tail recursion. In that case, we often have an extra variable, or we usually have an extra variable called the accumulator, and that's the place where we accumulate the result. It's like a variable in an imperative program. At each call, the value changes, and the final value of that accumulator is the result we're looking for. So, let's see what this tail recursive definition says. It says the sum of x's is the sum now with two arguments of x's and 0, and that second argument is going to be where we accumulate the result. Now the sum of an empty list, sum of empty list and s, we just return the value we've accumulated, that's s. Otherwise, if we've got the list x cons x's and the sum so far is s, then we replace that with a call, we strip off the x and add it to the sum so far. So we get sum of x's and second argument is x plus s. So let's see how that works out if we try an example. What is sum of the list 3, 1, 16? Well, it's the two argument sum function with the list 3, 1, 16 and the second argument, the accumulator 0. So we use the second of the two clauses for sum, and that says it's the sum of the list with 1 and 16 in it, and the second argument is 3 plus 0. If we work that out, that's 3. Now we've still got a non-empty list in the first argument, so we use the second clause again. X matches 1, X matches the list with 16 in it. So this becomes the sum of the list with just 16, and the accumulator now is 1 plus 3, which of course is 4. Now finally we've got a sum with just 16 in it. That again matches, just like in the direct recursion, that matches x cons empty list, so 16 cons empty list. And so what we do is remove the 16 and add it to the accumulator, and so we get the sum of the empty list and 16 plus 4, which of course is 20. And now we've got an empty list, no more numbers to put into the accumulator, and 20, so the answer is 20, according to the first of those two clauses. And of course that is the answer. It would be the same as what we would get with the direct recursion. 3 plus 1 plus 16 is indeed 20. So you've seen that we build every list by applying cons to a list and an element, starting with the empty list. And you've seen how we can define functions directly using a direct recursion, or we can use a tail recursion. So as other examples for you to think about, and we'll be looking at these in the next activity, you can think of defining a product of a list of numbers, or the maximum of a list of numbers. And we'll see in the case of maximum, we'll vary the template for recursion a little bit. So there we are. We've seen definition by recursion, direct and tail recursion over lists. So over to you now for an activity.